Alright, so when we're dealing with evens and odd functions, we're dealing with symmetry. So from a graph, it is very obvious what they're symmetric about. So for an even function, they're going to be symmetric about the y-axis. And for an odd function, they're going to be symmetric about the origin. The odds are easy because the O's go together, so if it's odd, it's symmetric about the origin. Even, symmetric about the y-axis. Nothing symmetric about the x-axis. So if we're looking at this graph, we've got a negative x squared, basically. So then if we were to flip it or fold it along the y-axis, it would line up. That means that this is y-axis symmetry or an even function. Second one, we could fold it across the y. It's not going to match because this point would fall right there, which is not on the graph. If we rotated it 180 degrees, this point would fall here, but this one's going to come down to that, which is not a point on the original. So this is just none or neither type of symmetry, neither even or odd. And then my last graph folded across the y-axis, not going to match up. If I rotated 180 degrees, this point would fall here, that would fall there. That makes this an odd function, which is symmetric about the origin. Then when we deal with equations, I think they're just as easy. One thing to remember is if you plug in a negative x, wherever you see an x, you look at what happens to the signs, whether they change or stay the same. If all of the signs change, that tells me it's odd, and I remember that because they're both 3 letters. If you plug in a negative x and none of the signs change, it's even, and I remember that because they're 4 letters. So to this day, I still remember all odd, none even, and it helps to write it out sometimes so you can see. So now for A, what we're going to do is we're going to take a negative x, and we're going to plug it in wherever I see an x. Negative x squared becomes positive x squared. This is my equation that I'm going to compare to the original. So none of my signs changed, which makes this an even function. If I go to B, I'm going to plug in a negative x, and I'm going to cube it, minus 1. So a negative x to the third is going to make it negative x cubed minus 1. And you just have to be careful. So my first sign changed, so sometimes people will see that and they think, oh, all the signs changed, that means it's odd. But then if you look at the second term, negative 1 stayed negative 1, so this would definitely be neither. You have to be careful with the constants. There's nothing that's going to make this negative 1 change to a positive 1. If we go down, let me erase this right here, and we do letter C. So I'm going to plug in a negative x cubed minus negative x. Negative x cubed becomes a negative, so I'm going to pull that negative out to the front. And then a negative times a negative is a positive. Now if we look at my original, we flip from positive to negative and negative to a positive. This tells me all of the signs changed, so this would be an odd function. And then the last one is a little tricky, absolute value. If I take the absolute value of a negative x, that's just going to give me, oops, that should just be an x. So my signs are not changing, none of them changed. This would be an even function. Another trick you can do is if you know what the shape of these graphs are, like for instance, if we have x squared minus 5, you're going to learn about this in a few slides here, but that's just a parabola shifted down 5. You can see, oh yeah, that graph is symmetric about the y-axis, that's even. You're going to learn about the absolute value. This is a parent function. It's just a sharp point. It's like a V graph, that's even. X cubes are going to be something like that, like the S curve, but we're shifted down 1, which makes it no longer odd. And then my 5x cubed minus x, that's another x cubed, the S curves, which this one is symmetric because it goes through the origin.